In section 3.2, we're going to be looking at, as you can see here, null spaces and ranges. There's a really important theorem that comes from this section. So let's get started. We'll start by defining what a null space is. And here I can see I don't have the word highlighted. So let's just read the definition for T. So remember that the script L with the V and W right now? That's the set of all linear maps. So for T being a linear map, the null space of T, denoted null T, is a subset of V consisting of those vectors that T maps to 0. Right, so null T has like formally this set notation, but here they should be underlined and highlighted. This is the definition of the null space of T. And we can take a look at some examples to kind of like see what that looks like. So first one, if T is a 0 map, we saw this in the last lecture, the 0 map. If T is that 0 map from V to W, then for every vector in V, T times V is equal to 0. What does that mean? That means that for all vectors V and W, well, this function, this linear map just maps it to 0. Therefore, the whole space V is equal to the null space of T. So I guess in picture form, we can draw like this. This is V, this is W. And let's say this here is element 0. All these vectors, V1, V2, V3, all of them get mapped to 0. So this whole space V is the null space of T. So we take a look at another example. So another example is, we suppose D is a linear map from the polynomials to the polynomials. We've seen this example before. It's a differentiation map such that D times the polynomial P is equal to its derivative. So that's what the function does. And the only functions whose derivative equals 0, as you probably know from calculus, are constant functions. So the null space of D equals the set of constant functions. And so again, like a little picture to kind of help you out. Constants, let's say these are the constants, all the constants, real numbers. And over here we have all the polynomials that aren't constants. And then we have, oh, so this is a vector space V, the W, and the element 0 is right here. So these all get mapped to 0. So the null of D is equal to this circle here, constants. Right, so it's basically the little subset or the vectors in V that get mapped to 0 and W. That's what the null space is. And you've seen this before if you've taken like a matrix algebra course, but we're going to be going over some interesting theorems. But first, another example is T, where T is a linear map from the polynomials to the polynomials, and where we multiply the polynomial by x squared. Right, so any polynomial P of x, we just multiply by x squared. And the only polynomial P, such that x squared times that polynomial is 0, is the 0 polynomial. So the nullity, or the null space of T, is just the 0 polynomial. And if you want to draw a picture for that, it'd be pretty much just a point of V that's in the null space. So now we can move on to a theorem. So suppose T is a linear map from V to W, then null T, the null space of T, is a subspace of V. If you remember from chapter 1, I believe, there are only, or was it chapter 2? There's only 3 conditions to check that something is a subspace. We're going to be going over those 3 conditions. First, because T is a linear map, we know that T of 0 is equal to 0. Right? We got that last theorem in the previous lecture. So 0 is in the null space of T. So again, one condition is that the 0 be in the subspace. The others are that addition is closed and scalar multiplication is closed. So suppose U and V are in the null space of T. Then T of U plus V is equal to Tu plus Tv by the homogeneity of, by the additivity of linear maps, which is equal to 0 times 0 plus 0, which is equal to 0. So why is this equal to 0? Well, because U is in the null space of T, right? So this maps to 0. Similarly with the V. Okay, therefore, addition is closed in the null space of T. Oh, there it is. Closed under addition. And now suppose U is in the null space of T and lambda is a constant in F. Well, then this equation here holds true. T times lambda of U is equal to lambda times T of U, which is equal to lambda of 0, again, because this gets mapped to 0 because it U is in the null space, and therefore equal to 0. Therefore, lambda times U is in the null space of T, so it's also closed under scalar multiplication. So they're saying we've shown the 3 properties. Therefore, the null space of T is indeed a subspace of V. So nothing that isn't really straightforward. Just kind of remember the null space is a subspace, and it's all vectors that map to 0. So next, we're going to be talking about something new. Not new, I should say. This should be really, you should be familiar with this, and it's injective, or some mathematicians say one-to-one. A function t from v to w is called injective, or one-to-one. If t of u is equal to t of v, implies that u is equal to v. A lot of the times we show this using the contraposition, meaning u not equal to v implies tu is not equal to tv. You can use either, they both work. So we have our theorem, let T be a linear map from V to W, then T is injective if and only if the null space of T is equal to 0. And I mean, that should make sense. If we have anything other than 0, like if we have 0 and something else, well then 2 things are getting mapped to 0, so it's no longer one-to-one. But this is a biconditional proof, so let's go ahead and prove this. First, suppose T is injective, and we want to prove that the null space of T is indeed 0. Well, we know that 0 is in the null space of T, right? Since the linear maps take 0 to 0. So now suppose V is in the null space of T. Then T of V is equal to 0, which is equal to T of 0. So V must equal 0, right? As it says there. And again, this here, TV is equal to 0. Well, because V is in the null space of 0, and by definition, it gets mapped to 0. Therefore, we can conclude that null T is equal to 0 as we wanted to show. Now suppose that the null space of T is equal to 0. We're going to show that T is injective. So suppose U and V are vectors in V, and T of U is equal to T of V. Now we need to show that this implies that U is equal to V. Well, 0 is equal to TU minus TV, since TU is equal to TV. And we can use the additivity property of linear maps. So U minus V is in the null space of T, which equals 0. Therefore, U minus V is equal to 0, which implies what? Well, that U is equal to V. Therefore, T is injective, and we are done with our proof. Well, if we're talking about injectivity, you should probably know what's coming up next. Okay, so next up we have the definition of range. Some mathematicians, instead of saying range, say image. So the image of a function, the range of a function. But like I said right now, we saw injectivity, so something's coming up, but we do need to define range first, and actually a theorem that comes along with it. So for T, a function from V to W, the range of T is a subset of W consisting of those vectors that have the form TV for some V in V. So the range of T is equal to that set. And this is a definition we learned in high school, maybe not defined as formally as this. Maybe in high school you just heard that the range was a subset of the reals, because most of our functions, if not all of them in high school, were from the reals to the reals. So that's what the range is. So an example, if T is a 0 map from V to W, so in other words, all vectors get mapped to 0, well then the range of T is just 0, because that's all we're mapping to. Suppose D is a linear map from polynomials to the polynomials, and it's the differentiation map defined again. D of a polynomial is equal to its derivative, P prime. Well, because for every polynomial, Q, there exists a polynomial P such that the derivative of P is equal to Q, well, the range D is still all the polynomials. In other words, give me a polynomial, and I can find you another polynomial such that the derivative of that polynomial was equal to your original one. So here the range are all the polynomials with real coefficients, real valued coefficients. And now we introduce a theorem. If T is a linear map from V to W, then the range of T is a subspace of W. So not only is a null space a subspace of V, but range of T is also a subspace of W. So proof for this one, nothing complicated, just showing there are three properties again. So suppose T is a linear map from V to W, then T of 0 is equal to 0, which implies that 0 is in the range of T. Therefore, we have one property down, two more to go. Well, if W1 and W2 are in the range of T, well, then there exists V1 and V2 of V such that mapping those, I guess the image of V1 and V2 get mapped to, or the image of V1 and V2 are W1 and W2. Well then, using additivity again, T of V1 plus V2 is equal to T of V1 plus T of V2. which is just equal to w1 plus w2. Therefore, w1 plus w2 is also in the range of t, so range of t is closed under addition. And finally, is showing that it's closed under scalar multiplication. If w is in the range of t and lambda is in f, then there exists vector v in v such that the image of v is w. Therefore, t of lambda times v is equal to lambda times t of v, which, since this gets mapped to w, we have lambda w. Therefore, lambda w is in the range of t, which shows that range of t is closed under scalar multiplication. Thus, range of t is a subspace of w. Now we define what I was foreshadowing to, which is the definition of surjective. Here I should have had it highlighted. Actually, that should be in green. So a function t from v to w is called surjective if its range is equal to w. In other words, if the range is equal to the codomain. An example, this should be like a non-example. The differentiation map from polynomials with degree 5 to polynomials with degree at most 5, I should say, is not surjective. Why not? Well, because polynomial x to the 5th is not in the range of d. Right? There's no polynomial in our domain for which its derivative will equal x to the 5th. However, if we were to map polynomials with at most degree 5 to polynomials with degree at most 4, this is surjective. So we come to our fundamental theorem of linear maps. Suppose V is finite dimensional and T is a linear map from V to W. Well, then range of T is finite dimensional and the dimension of V is equal to dimension of null T plus dimension of range of T. So to prove this, I'll draw pictures along the way to kind of help our intuition. So let U of 1 to UM be a basis of the null space. So first of all, I'm going to draw the V here. And the null space, let's draw it in blue. U1 to UM is a basis of the null space. So because we have m many vectors, the dimension of the null space of T is m. And this we can, by a previous theorem we saw in chapter 2, we can extend this to a basis of V by adding those vectors to the list of V1 to Vn. So V1 to Vn to ... Vn are a basis of what's in red, or I should say everything contained in V that isn't the null space. Well, then the dimension of the whole V is equal to m. That's coming from here. We have m many vectors in the null space. That's a basis of the null space. And n, which is the basis for the rest of the space that isn't the null space. So that's why the dimension of V is equal to m plus n. So to complete this proof, we're going to show that what? That the range of T is finite dimensional and it equals this n. So to do this, we're going to be proving that TV1, T of V1 to T of Vn is a basis of the range of T. So let V be a vector in V. Well, because U1 to UM and Vn to Vn spans V, we can write every vector in V as a linear combination of all these vectors where all the A's and all the B's are scalars in F. Well, applying T to both sides, we get that T of V is equal to this linear combination B1 to V1, B1 times T of V1 plus dot 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 all the way to bn times t of vn. But wait a minute, what happened to all these vectors? Well, remember, u1 to um are all in the null space, so they all got mapped to 0, therefore we can exclude them. That's why it says here they each disappeared because they were in the null space of T. So now, the last equation implies that this equation above here, right here, implies that T of V1 all the way to T of Vn spans the range of T. So particular range of T is finite dimensional. So to show that T of V1, the list all the way to T of Vn is linearly independent, suppose C1, these scalars C1 to Cn are in F, and that this linear combination is equal to 0. Remember, how do we show something's linearly independent? We show that the scalars must equal 0 for that linear combination to be equal to 0. Well then, T times the linear combination is equal to 0, right? We're just moving things around. I guess in a way factoring out that T, even though it's not a scalar or anything. And therefore, that linear combination is in the null space of T. And if it's in the null space of T, because u1 to um spans null T, the null space of T, we can write C1 times V1 all the way this linear combination. Okay, let me erase here and color code stuff because things are getting confusing. So this here is in the null space of T, and because u1 to um spans null T, we can write this linear combination. So because this, we can write that as a linear combination as well, such that they're equal, where all the d's are scalars in F. But this equation then implies that all the c's and d's are 0. Why? Because all the vectors u1 to um and v1 to vn are linearly independent, right? They were a basis, so they're linearly independent. Therefore, t of v1 to t of vn is linearly independent, and therefore basis of range of T as we needed to show. So fantastic theorem, really important one. It is a fundamental theorem, just as you've heard maybe in your calculus class, a fundamental theorem of calculus. They are really important theorems. And now the last section is, we're just going to be looking at 4 theorems, something you may have seen before. So here, suppose V and W are finite dimensional vector spaces such that the dimension of V is greater than the dimension of W. Well, then no linear map from V to W is injective. So our proof, pretty easy, are straightforward. Let T be a linear map from V to W. Well, then using the fundamental theorem of linear maps from the last section, we set up the equation. The dimension of the null space of T is equal to the dimension of V minus dimension of range of T. So here we kind of move stuff around from the fundamental theorem of linear maps, but we get the equality nonetheless. And the dimension of null T, or sorry, this here, is greater than or equal to the dimension of V minus the dimension of W, because this, if anything, is greater than or equal to this. That's why we get that inequality, which is greater than 0. Therefore, the dimension of null space of T is greater than 0, and we had stated before that for it to be injective, the only thing in the null space of T should be 0, so it should have dimension 0. And this means that null space of T contains other vectors other than 0. So T is not injective. Another similar, I guess, a twin proof, or a twin theorem, I should say, is we suppose V and W are finite dimensional vector spaces, such that now the dimension of V is less than dimension of W. Then no linear map from V to W is surjective. And again, pretty straightforward proof. We're going to use the fundamental theorem of linear maps. Let T be a linear map from V to W. Well then, again, switching things around from the fundamental theorem of linear maps, we get this equation, dimension of range of T is equal to the dimension of V minus the dimension of null space of T. And that should be less than dimension of V. Again, because we're subtracting something, if anything, which is less than dimension of W by assumption. Therefore, because the dimension of the range of T is less than dimension of W, the range does not equal the codomain, meaning that T is not surjective. So using this, we can prove actually two theorems that I know you've applied, or actually I don't know, but you probably have applied in your classes. A homogeneous system, if you don't remember, a homogeneous system is a system of linear equations such that the right-hand side of the equation is equal to 0 for all equations. So a homogeneous system of linear equations with more variables than equations has non-zero solutions. So let T be a linear map from Fn to Fm. We have a homogeneous system of m linear equations with n variables. From the theorem above, this theorem over here on the left, we see that T is not injective if n is greater than m. Or in other words, if we have more variables than we do linear equations. So it's not injective. So we get more, we have non-zero solutions because obviously the trivial solution, all x's being equal to 0, is a solution, and it's not injective, so we get more solutions than that. So that's how we can guarantee that we have a non-zero solutions. Similar thing, an inhomogeneous system where they don't equal 0 anymore of linear equations with more equations than variables has no solution for some choice of the constant terms. So, similar proof, let T be a linear map from Fn to Fm. We have a system of m equations with n variables, but now m is greater than n. And the theorem on the top right tells us that T can't be surjective if that is the case. Therefore, the theorem holds. And this is where your professors get that whole, tip, right? That if we have more variables and equations, you must have a non-zero solution. In matrix algebra, you may have seen this. This can be proven with something called the Gaussian elimination. But knowing that the theory of linear maps makes our life a whole lot easier because those proofs are pretty involved or pretty lengthy, even though they may not be too difficult to understand. And here we just proved 4 theorems without saying, I guess without writing much, but saying a lot.